Hello, welcome again. We are covering the topic gas turbine cycle for civil services name IFS and gate aerospace exam. Now we'll cover a subtopic under this main topic named as reheat cycle. Okay. So this uh, was a simple cycle 1, 2, 3, 4 on PS diagram that we have studied. 1, 2 is isentropic compression that is done in compressor. Then 2, 3 is heat addition at constant pressure that is done in combustion chamber. 3, 4 is your isentropic expansion that was done in turbine, and 4, 1 was heat rejection. Okay. So now if we split this turbine expansion, suppose we split it here and take the gas and reheat the gas. So we have taken this gas here and then reheat it to temperature T5, and then we expand in the next turbine, then this will be a reheat. We are not expanding the gas throughout from 3 to 4 dash. We are taking the gas from the first stage and reheating the gas to 2.5 and then expanding it in the next. So this is your reheat. So by doing this, previously the work done was 3 to 4 dash. This line. This line was representing the work done, or the temperature drop was T3 minus T4. Okay. But now the work done is from 3 to 4, this, and from 5 to 6. So as we can see that these are the constant pressure line. This is constant pressure line, this is constant pressure line. Here the gap is less and here the gap is more. As the constant pressure line diverges from each other, so work done or the specific work done or specific work obtained with the reheat cycle will be more. That T3 minus T4 plus T5 minus T6 will be more than T3 minus T4. That's why the work done will be, or specific work done will be more in case of reheat cycle. Okay. So I am reading this out. A substantial increase in specific work output can be obtained by splitting the expansion and reheating the gas between high pressure and low pressure. So initially it was this cycle. Now we are splitting the expansion and reheating the gas in between. So we are able to increase the specific work output. The figure shows the relevant portion of the reheat cycle on PS diagram. That the turbine work is increased is obvious when one remembers that vertical distance between any pair of constant pressure lines increases as the entropy increases. So here the vertical distance is this much. So as entropy increases, the vertical distance becomes more, or we can say T5 minus T6 is more as compared to T4 minus T4 dash. That's why the work done is increasing. Or we can say T3 minus T4 plus T5 minus T6 is more than T3 minus T4 dash. So that's why the work done or specific work output will increase. So now the specific work output is, this is the work done by high pressure turbine, this is work done by low pressure turbine, and this is the work required by compressor. Okay. So as you can see, we have to subtract this. Okay. So now if we assume that the temperature of reheat is same as that of maximum temperature, then T3 will be equal to T5. Okay. Then this expression can be read Cp T3 minus T4 plus Cp T3 minus T6 minus Cp T5 minus T4. So now if we divide both sides by Cp T1, then it will be W by Cp T1, and this will be T3 by T1, and this will be T4 by T1, this will be T3 by T1, this will be T6 by T1, this will be T2 by T1, and this will be 1. Okay, now this is T3 by T1, this is T3 by T1, so they will get add, so it will be 2 T3 by T1. So now we can divide this term by T3 and multiply it by T3. This will be T3 by T1 and this will be a T4 by T3, but T4 by T3, or we can say T3 by T4 is equal to pressure ratio of first turbine rate for gamma minus 1 by gamma, isentropic ratio. So T3 by T4 can be written as, or T4 by T3 can be written as, pressure ratio of first or high pressure turbine is R. It can be written as R1 rate for minus gamma by gamma minus 1 by gamma, and this T3 by T1 can be written as T. Similarly, for this part we can divide it by 5 and multiply it by 5, and then T6 by T5 will be a R2 rate for minus gamma by gamma minus 1 by gamma. Okay. R2 is pressure ratio of second or low pressure turbine. Okay. And T5 by T1 is the T, because T5 is equal to T. And now this T2 by T1 is the R gamma minus 1 by gamma. R is overall pressure ratio. That means R is equal to R1 into R2. That is for low high pressure, that is for high pressure, and that is overall. Okay, so this expression will become 2T minus T divided by R1 rate per gamma minus gamma minus T, R2 rate per gamma by gamma minus R gamma minus by gamma plus 1. Okay. Now R2 into R1 is what? R. So this R1 can be written as R1 by R. Okay. So here now the work done expression is in terms of P, R and R2 only. Okay. Suppose T is constant and overall pressure ratio is also constant. Now only variable will be R2. So if we differentiate it with respect to R2, then we can get the condition for maximum work done and put it equal to 0. So this will be 0. This will be a minus gamma minus 1 by gamma T divided by this R gamma minus 1 by gamma into, we are differentiating this to R2 gamma minus 1 by gamma minus 1, and here it will be T is already there, gamma minus minus plus gamma minus 1 by gamma R2 minus gamma minus 1 by gamma minus 1. Or further solving it, we will get R2 is equal to root R. Okay. But R1 into R2 is R, so R1 will also be equal to root R, or we can say the pressure ratio in high pressure turbine and in low pressure turbine is same for maximum specific work output. So now if we take, suppose this complicated term R gamma minus 1 by gamma as C, then we can write the expression for maximum specific work output in terms of R and T, because for maximum specific work output R1 and R2 is equal to root R, putting it equal to root R. Here R1 was there, here R2 was there, so now we will compute them as root R. Okay. So solving it, so we will get 2T minus 2T by root R gamma minus 1 by gamma minus R gamma minus 1 by gamma plus 1, and this is your T. So specific work output will be 2T minus T minus 2T root 3 minus 3 plus 1. This is your specific work output.